Yeah, it's recording.
Yeah, yeah,
Okay, so hi everyone. Welcome to another session from SD Skills on the CTCI, that is a Cracking the Coding Interview book club. Today we'll be discussing a chapter on linked list. Okay,
yeah.
so let me share my screen, the OneNote. Okay, so linked list actually is a very okay. First of all, is my screen visible?
Yeah, it's really.
Okay. So linked list actually is a very easy chapter topic, right? But it can become complex in some very, what do you say, very simple cases also, right? Once if we are stuck somewhere, right? So it's always better to redo it properly, right? So that is what most of the things, most of the places mentioned that way. So in this book, it's also pretty simple. So we'll go through three problems. One is remove duplicate, second is a partition problem, and third is the intersection. And if you find time, we'll go with another one, right? So we'll just focus on linked list for today. Okay. So the
Yeah.
first problem about removing duplicates, okay. The problem statement is write a code to remove duplicates from an unsorted linked list. Okay. So it is easy to remove duplicates, many duplicates, n number of duplicates from a sorted list, but it's not so easy uh, to remove duplicates from an unsorted linked list. So we'll have to take help of some data structure or something, okay? Or maybe the time complexity will increase or the space complexity will be more, so it won't be more efficient. But so what are the different ways you guys think about we can remove duplicates in a linked list?
So I think if you take that temporary buffer is allowed, I mean, if it is allowed like extra space, like you can create a dummy node and just while traversing the node, just check if it is first time you are encountering, then append it to the new node, like the new linked list code which you have created, right? I
Okay,
mean, extra space you'll have to take for that.
right, right. So you were
Mhm.
saying that you just traverse through the linked list, okay, and then whenever you encounter something which is not encountered earlier, you just create another list and return it, right?
Yeah.
Yeah, so that's a fair thing, you know. But actually, in the book, they have described two approaches, and one is similar to yours. I think both are almost similar, but you actually combine both of them together, it seems. So the first thing what it talks about is like, you know, when you want to remove duplicates in a linked list, you have to track duplicates, right? So there are different ways to trap duplicates. Okay, one way is you can use another data structure like a hash table. Okay,
Yeah.
in C++, instead of hash table, I think you should use hash
Set,
set, right?
yeah, set would be much more
Yeah,
because we don't need any key value pair here, right?
correct, correct.
Mhm.
So if we use like an unordered set in the case of C++, we can just iterate through the whole linked list. Okay, and then we keep on pushing that to the set in case if it's not present in the set, or if it's present in the set, we just avoid that, okay, or delete it, right? Okay, so that's a very pretty simple thing. So let me share my lead code playground where I've actually uh, okay, so I did not open it. Oh man. Okay, just give me a minute, I'll have to open that.
Mhm.
Okay, I'm sorry about that. Yeah.
Yeah.
Okay, so yeah, I think yeah, it is open. Okay, that's good. Or else I'll have to go to the login and all that stuff, right? Okay. So here actually I've already have this code. Okay. So I didn't want to spend more time on all these small things, right? So this is our linked list data structure node. Okay. So I have a node, then it is data, and then it's the next node, and then this is my public constructor. Okay. So here, and these are some of the utility functions I'm using because it's not our normal lead code, right? So this is a
Yeah.
playground, so we have to have all the utility functions on our own. So removing duplicates, this is my first approach function. Okay, so I'm using a hash set here. So this is a hash set or unordered set. Okay, and I'm actually having another pointer which is called as previous. Yeah, so this also small things becomes very important in linked list, right? So we cannot, we can, or I'm not sure, but just with a single pointer. So this is an input pointer that is will be our head of the linked list, which will pass by the main function, and we are using an additional pointer. Okay, and then we are traversing the whole linked list, and at every point, okay, so this is just a pointer. I am actually pointing to a node which I want to delete, because in C++ we have to explicitly delete it to avoid all the memory leaks, right?
Yeah.
So in this, this is the hash set. Okay, so this hash set, I just find if my uh, value of current node is present. Okay, so if it is present, right, so then I mark that this node to be deleted. But before that, I actually move the pointer of the previous one to the next one. Or else, if I find it already, if I don't find it, so I insert that in my hash set, and then actually mark this node as my previous node. So next time when I come here, okay, and when I find it is already present, I can just walk over, or maybe just point to the next node, right? And
Hey,
here is, yeah, sorry, but
is
Leon,
that already sorted?
No,
The link
unsorted.
list?
no, it's not sorted.
Then
That's
how
why we
you
are using
know the
hash set.
previous? The previous, you check for the previous and the next. Oh, okay. Okay, I see.
Yeah.
Oh, you
So,
need the previous so you can delete the node, right?
right, right, right.
Okay, got it.
Yeah. So this is not sorted, and therefore we need one more pointer actually to track the previous one, so we can actually jump over to the next one, right? And this is the one which I'm pointing for a deletion. Okay, and then when I come out of this if else loop, I actually delete it if it is true, if it is not null, right? So this is a very simple approach, but only thing is we are using an additional data structure here, right?
Yeah.
So, so the above solution time complexity is again linear, right? O of n, like the number of
Yeah.
least what we have, right? So, but the book also says the another approach would be like if we are not allowed for any buffers or any data structures, right? So, how do we do about that? Okay. So, without a data structure, how can we do? Any
Oh,
guess?
without set. Yeah, yeah, yeah.
Think we could do two for loop, right?
Huh? Yeah.
So one the outer for loop will point to the current pointer, and
Mm-hmm.
in the for loop, go forward, and then if it see the duplicate,
Mm-hmm.
then uh, probably if it see duplicate, it can go ahead and delete that duplicate,
Right, right, right,
and then
That would
it
be
keep going
n
all
square,
the
right?
way to the end. If they see duplicate, it keep deleted.
right. Good. Yeah. Yeah, exactly. So yeah, yeah. Sorry, Shashank, what was that?
I'm saying, but again, it will become n square, right? We are
Yeah, 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 yeah,
Right?
reducing the
Yeah.
time
yeah.
complexity. Yeah.
See, yeah,
And
then it becomes like this, right? Either space complexity or time complexity, whatever is more important.
Then this is far better, right? Time complexity. I mean, O of n is there on the cost of space, right? Here in the
it,
first approach,
Yeah,
on
I
the
think
cost of
Leon
space,
has
where
something to
it.
say. We'll come to that. Yeah,
uh,
Leon,
Okay.
what?
it would depend if you have enough memory or not. Yeah. Some case you don't have enough memory, then you have to go with the approach that cannot create extra memory.
Okay.
Right, right, right.
Yeah,
So
that's true.
if they say we want to sacrifice on the time complexity, but we have a very small memory footprint, so memory is more important in that case. So then a small delay or a lag is enough, is fine, you know. So it might be a very small linked list also. It depends on the input size, right? So in this case, we can actually go with the n square solution. It
Yeah,
depends on
then
what are test cases, right?
yeah.
Or our specific, yeah. That's right. It's n square, but that is another approach. We cannot actually avoid that. I'm not sure how much more we can do in that. Okay,
Yeah.
so for this also, I have already the code here. Okay, exactly what Leon said. Okay, but I'm not using for loop, I'm just using while loops. So this is my head, and I'm passing this one, I'm just storing this current, and I'm just running using this current as external loop. And then I have another pointer which will be which will point to the next list, you know, the next element of the list. So this actually is looking for the next element if it is not null, and then it's going to compare the data with the current data. So whenever I find that, okay, so I mark that as a delete node, and they just point this runner next to the runner next, right? So it is getting mapped to the next one, and then I delete this node, or else if I don't find that, I just keep on moving ahead, right?
Yeah.
In the runner dot runner next, and when I've completed this one, so I just move to the current
Next.
next. So that is the external loop. I'll just move ahead. Yeah, exactly. So what you guys said, it is exactly the way it is in square, and we have to use two loops, or else that won't be possible, right?
One more thing, the difference between the second approach and the first approach also that this one does not use the previous, right? You also need to delete the node, but you don't use the previous because you check the run the next, right, Santos?
Yeah, yeah.
And
So we are just using the runner, and then we actually just compare that. But anyway, we'll have to have a runner as well as current. Yeah. So we don't need
so
an additional pointer. Yeah.
yeah. So
Yeah, go ahead,
one
Jason.
more approach, what I was thinking, can't we use divide and conquer, like merge sort kind of approach? Break the entire list into single elements, and whenever you find they are unique, then you merge them. So n log n it will take then.
Yeah, yeah, yeah. That is a good approach too. So, but in that case, we are again using a call stack.
Oh, yeah, that's true.
So
Extra
call
space for merge,
stack,
but
yeah. So call stack usually takes more memory, I would say, because it has all those additional things to store than even a normal stack. So we can use a stack also, but again, there will be that additional data structure,
yeah.
right? Yeah, but we can make it more time, or maybe that is another approach. Yeah, right.
But implicit stack won't be considered as extra space, right? It is because once you are using, you are returning it back to the memory.
No, but if the list size increases, then
Then yeah, you may run out of the memory at times.
yeah, yeah, we may.
And I think also unless you have a special way to do it, normally the merge sort we need extra memory, like not only explicitly on the stack, but you need it to for merging.
External, yeah. External
Mhm,
space is
Yeah,
required
yeah,
for that.
not I'm not counting the stack memory,
mhm. Yeah,
Okay.
right?
yeah.
Hmm. Yeah, you're right.
So yeah, what you guys said, this was a good approach also, but this book actually talks more of the basic approaches, so therefore they have actually focused on only all those more simple approaches, right? Yeah, so but
Yeah,
we have been doing a lot of stuff, so yeah, that's good
right,
to
right.
discuss others also. Okay.
Because similar question like there is in lead code merge, how to merge two sorted two lists. So there we use merge sort kind of.
Right, right, right. Yeah, yeah. Okay, let's move on to the next one. So in this, actually, we talk about, is there something on the chat? No, right? Okay.
Mhm.
So this is another problem. They talk about partition. So what it says is write a code to partition a linked list around a value x, such that all nodes less than x come before all nodes greater than or equal to x. And if x is contained within the list, the value of x only need to be after the elements less than x. Okay. And the partition element x can appear anywhere in the right partition. It does not need not to appear between left and right partitions exactly. So that is why actually he shows a very weird way. So our partition in this input, okay, so we have this particular list, right? So we have to partition across 5. Okay. So what it's trying to say is you make this partition in such a way that the elements below 5, okay, are together, and above 5 are also together. But only the partition which we are talking about 5 should not be exactly between both of them. It can be anywhere, so you partition in such a way so the order doesn't matter, right? So that is what it's trying to say. This 3, 1, 2 are close together, and all the numbers which are less than or equal to 5 are all together. So we can have a partition in such a way. So this is what is the problem statement. So
In place of 10, 2 can come and 2 can go to 10th place, right?
okay, so I don't think so. They would, you know, appreciate moving or copying the values. Okay,
Okay.
that is what I think. It's not explicitly said, but I think this is a good thing to get it clarified. But as looking at the implementation, it doesn't seems to uh, focus on that. So it's like copying. Usually in the linked list, they tend to go with copying, unless in a case like when we are deleting a node, right? And we are pointing to the same node. So then in that case, it might be okay because there is no other option. But usually it is like you don't copy, but you use the complete, what you say, the address of the node itself, right? And then
Yeah.
you try to move them. So that is what may be a restriction here, though even it's not explicitly stated here. Yeah, so correct. So what we can do is 3, 1, 2, whatever the way you can do. So there are different ways to do it, right? So one is what was discussed in the book, like in the case, like if it, this whole list was an array, right? And then we were asked to do some shifting in the array. That is an expensive operation in an array shifts, right? Because in array
Yeah.
if you shift you have to shift everything, but in case of linked list it is much easier. So that is one advantage of using a linked list, right?
Yeah.
So so the way actually okay, are you able to see my screen, right?
Yeah,
Yeah.
yeah, that's
Okay,
fine. We can see your screen. I
okay,
can see your screen.
okay. Well, okay, I'll just go to my this one now. So how do you think about the approach to partition this? What is the approach you would think of? Any guess?
One is again like taking extra buffer, like create a dummy node and whichever elements you see lesser than 5, you try to append all those to the dummy node. I mean, you'll have to use extra buffer in this case, and all those elements which are greater than 5, after that you start appending, right? I mean, extreme brute force kind of, if we take.
Okay, so you are saying like we use some sort of a, okay, let me share my one node then in that case. So you are saying, so okay, let me draw, right? So we actually use, oh man, okay, maybe this is my node, right?
Yeah.
Okay, a dummy node or so. Okay, and then I just iterate through the whole list, okay, and
Mm.
then I compare with the partition 5, right? So if
Yeah.
any node with partition greater than or equal to, okay, I just append to my right side of this dummy node, correct? Or if
Yeah.
it is less than 2, then I append to the, okay, this is not
Left.
work. Yeah, work left, and then I actually shift my dummy node here, something like that, right?
Yeah. Kind of.
Okay. Yeah. Okay, maybe I should not say that. I just keep a node here, okay, and then keep on filling it. But I think that will be a very good approach, I would say. And yeah, it will be more time efficient as well as space efficient, right? Yeah,
No
that's a good approach.
buffer you will be using, right? Space you will take, right? Because extra node you are creating out of the given linked list, and to that you are appending given on the condition like which elements are lesser than 5 and which are greater than 5. So extra
Oh,
buffer you're using here, right?
so you are saying that we take uh, actually we split almost, right, the whole linked list in two parts.
Yeah, kind of.
One, okay, 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 yeah. And then you create a linked list, one linked list which will be for lesser than this partition, right?
Yeah, yeah.
And the second will be for greater than the partition. Yeah, yeah. Okay, that makes sense.
Uh, my
Uh-huh.
would be like reduce the delete node we have before. So the condition to delete a node would be when this node is less than the partition, and when we delete it, actually we not delete it, we just move it, to another uh, append, the delete node to another linked list, right?
Mm-hmm.
So at the end we have the leftover, which is greater than or equal to the partition
Mm-hmm.
on the current linked list,
Mm-hmm.
and the one that we delete and append it to another linked list
Mm-hmm.
will be the one that less than that,
Mm-hmm.
right? And then use the pointer, to point to the head of the second linked list.
Okay. Yeah. So you are saying that take one which is lesser than and which is greater than, make two linked list,
Yeah,
and just keep on
like
moving.
it just reduce the delete that delete
Right, right, right.
function that we have before.
Right. Yeah, that's a good approach. I think that is what actually the book also discusses. Yeah. So that's, we are on the correct path. So, okay. Oh, okay. I just, okay, no problem. So the way, as you guys rightly said, uh, so this is the partition function. So that is what the approach here is used in the book also. So what is trying to do is partition the
So
whole linked list.
screen
Sorry.
is not screen is not
Oh,
visible.
really? I'm sorry.
Yeah.
Okay. No, I did not share it. Okay. Is it visible now?
Yeah, fine.
Okay. So this is what the approach is. What it talks about is we want to partition this, and this is our input node, and then we are using 4 pointers. Okay. I think we can optimize on that, but for now, actually, what both of you guys said, it's like we can have two linked list. Okay. So what it is doing is before start and before end is one linked list which will have all the nodes which are lesser than the partition, and after start and after end, these are the start and end pointers of the second list which are greater than or equal to the partition, right? So just to go through the list one at a time. Okay, and then this is the next node which I'm just is being stored here. Okay, and then the current node you just remove it from the list by setting its next to null. Okay, and then compare its value. So if it is less than the x, then actually we have to put on the before list, right? And if my before start itself is null, it means it's the head. So we just point to the head. And for now, the end also will point to the same node, right? But if we are in the middle, we can always know that we have to actually move the tail in that case, right? So the before tail will be moved, and then we will be, okay. So we'll add to the tail, and then we'll move the before end, that is the tail here, right? So this is the one which will be for the lesser than x, and here it is exactly the same implementation for if uh, greater than or equal to the partition value, right? And then at the end, so okay, so this is the way we iterate the whole node, right? At the end, we just actually, okay, if there's one more condition to check, if I don't have before start is equal to null, then you just return the after start because there is nothing on the before. So we have only one list, right? Or else we actually merge like the tail of the first list to the head of
Right.
the second list and then return the before start. Okay. So this is the very simple approach, and actually you just divide the whole list in two parts and then merge them. Okay. So this is one approach. So what do you guys think about any other approach?
We
So because
Uh,
some
sometimes, go ahead.
this
no,
is
no,
not the approach that, sorry, talk at the same time. Go ahead.
Okay, yeah,
it,
yeah. Shashank was saying slightly different version of that. Yeah, right. So that might be the, yeah, go ahead, Shashank, if you want to talk about that.
No, I was saying like, can we use a quick sort like we are using, right? Keeping a pivot and then shifting the pointers in case of array.
Okay, yeah, so you are actually talking the similar way, right? But
Yeah,
actually, if you look at this one, the first approach, what they talk about, we have 4 pointers, and that is what we are more concerned about, right? And the
exactly.
second is, if you look at this, and if I even run this, so what happens, this is a stable sort of partitioning, right? Because the order and all those things is not being changed, right?
Yeah.
So therefore, this is a better way to do. Okay, so I'll just run this, and if you see, this is my partition one, and if you see the order, so three, okay, two and one. So two is here, right? Two and one. So they are actually in the same order, as well as this one, 5, 8, 5, 10. Okay, so the order is not changed. So this is sort of a stable partitioning.
40.
Yeah.
Mm.
So that is the only difference it talks about. But as you said, you can use some sort of pivot sort of thing, right? And then we keep on partitioning it, correct? So
Yeah.
then, so the pivot will be like you just use some dummy node, right? That is what you were talking about earlier. Okay. So you don't
Yeah.
want to split it, but use same two nodes here, head and tail, and then just recurse through the whole list. Okay, and then you just mark it. So if your value is less than your current this partition value, and then so you append it before the head, right? And then you keep on moving the head. And if it is greater than, okay, so you just append it to the tail and then keep on moving the tail. And then this is our tail, and then we just return the head, correct? So
Mhm.
this is also a very simple way to implement. But yeah, sometimes it becomes very critical to even come up with this. Yeah, but it looks very easy also now, right? And it's very optimal because of, and we don't have to do splitting and then merging and everything, right?
Yeah.
But it's not stable order, right? It's like
Yeah,
kind of reverse space of
correct.
a stable order.
Right. So that is the only one downside of it, or else, but this is also not a bad approach, right? And it's very quick to do. If you're not concerned about the order, then this is most optimal one, right? Yeah.
I think interviewer will definitely put, I think, restrictions if
Mm.
like we go by
Yeah.
this way. Yeah.
So we'll actually have to discuss both the ways, right? Means at least we'll have to prepare all the ways, so all the approaches as possible. So we have to, in case if he talks about that, then we should be able to come up with the next one. So for us, no approach is good or bad. Everything is okay, right?
Exactly.
Yeah. So if we see here, as the stability is not the same as it was earlier, right?
Yeah.
So the order has changed. It is 1, 2, 3, and then some 5, 5, 5, 10. Yeah. So that's the only difference in this. Okay.
So
So,
my approach was a little different because I,
oh really? Okay.
delete that
Sorry.
would delete the node, right? So kind of like you remove duplicate, but in this case, get think about duplicate is
Mm-hmm. So,
yeah, I think I like
mhm.
okay, my approach is same as the first approach, but only need 2 pointer. Yeah,
Yeah.
that's
Oh,
my
you were saying just use 2 pointers instead of using 4 pointers, right?
yeah, yeah,
You just split it
yeah,
into.
yeah.
I think that also should be possible. But then, okay, so then in that case, okay, if we can go back on this one, but how are we actually going to uh, take care of the merging part then, right?
Because you only track the one that less than uh, the partition, right? The one that the remain one have to be the one that already greater than or equal to partition. See,
Mm, yeah. No,
so
but
like let's think
uh,
about the before start and end start. You only handle that. You only you know but the after you don't need, because the after is the remaining is still in the original uh, uh, linked list,
Okay, okay.
because
Oh,
what,
yeah.
you only delete the one
Hmm.
that is less than the partition, and you
Okay,
move that one to the end of the, to the before, you set it to the before end.
okay. So you are saying just iterate through the original list, remove only the ones which are lesser than the partition and form a separate list. Okay. And then when you are deleting the original list, you maintain the list as is, right?
Yeah,
And then you merge the both. Yeah, yeah. Okay. That is also a very efficient way of doing it. Yeah. Okay. Yeah. That's good. But you'll have to only take care of how you delete it, right?
right. Yeah,
Yeah. Okay. Hmm.
the same way that we remove duplicate, right?
Right, right, right.
Yeah,
So it won't be a deletion. We just have to move that, okay? But we just remove the node physically and attach to this list. Okay, we don't have to create any additional node. Yeah. So
and
that's
you still
good.
need to delete it, because it's still, if we don't, it still belong to the original one, right?
Yeah,
So
yeah,
we
but
have
we
to,
can use the same node address.
yeah,
Yeah, yeah,
yeah, yeah. We have to reduce the same node
yeah,
address.
yeah. That's good. Yeah, that's a good approach too. Yeah. Okay. So our next problem here is about intersections now. Okay. Uh, okay. So what it talks about intersections. So it says, given two singly linked list, determine if two lists intersect. Okay. And return the intersecting node. Note that the intersection is defined based on reference and not the value. That is, if the kth node of the first linked list is the exact same node by reference as the ith node of the second linked list, then they are intersecting. Okay, so the example what, okay, I'll just write it here. Okay, no, this one, okay. So one is like if we have a list something like 3, oh, 3, 1, and then if I have 5, okay, and then this is 9. Okay, and then this is my list actually goes to 7. Okay, 7, and then this goes to 2, and then this goes to 1. Okay, and then I have another linked list which is actually intersecting here. So it is pointing to 4, 6, and this is what actually is in the example also there. So if we have this linked list, so one is starting from, this will be an H1, maybe head 1, and this is H2, right? So if we have two such linked lists starting from H1 and H2, okay, so then they are intersecting, so we need to return this 7. Okay, so what do you guys think about how and what are the best ways to do this and how we can do this?
So one way would be like you calculate the length of both the list and get the difference, right?
Right,
And
right,
which is longer in size, you move the pointer of the longer linked list till that difference. And when both the pointers are at same point, parallelly you move and check the address. At whichever point you hit both are same, will return that particular node. But there will be two passes, right? One pass for calculating the length and then other pass for parallelly moving both the pointers.
correct, correct, correct. So what he in this books talks about first is actually if first we need to determine if there is an intersection. Okay,
Oh, yeah, yeah.
so this book talks more about being methodical and all those stuff, right? So all
Yeah.
the step by step approaches, the basic way how we would approach it, right? So sometimes these things are also very important, because if the problem statement is very easy, it means that they are looking for some other stuff also, right? So that is what Asim was talking about last week, right, in one of the session. So here actually it says that we need to actually detect if the two lists intersect. So one approach would be use an hash table, right, or a hash set maybe. Just put one of these string which starts from maybe h1 or h2, either of it, put in a hash table. Okay, the whole of that start from 3 maybe from here, and then to 1, run to 1. So put that in the hash set, and then you start from h2. Okay, and then always look when you're starting traversing from h2, so always try to look in the hash set if there is a node present in that, the current node is present in the hash set. So as soon as it hits on 7, right, so you know that it will be there in the hash set, right? So we can always return from here. So that is one way of doing it. Okay, but only in the hash set you are not going to store the values. You'll have to store the address of a linked list node, right?
Yeah.
So memory location, yeah. But but the way you said was actually a good approach, because we are avoiding using a data structure, correct?
Yeah, absolutely.
Yeah. So then, as you said, like you see if both of the linked lists first actually have the same last node, because there might be these two linked lists, they are not intersecting at all. They are like they both are parallel. In that case, what it says is first you need to traverse both of these lists and go to the end. Okay, and at the end you compare those two tails of both h1 and h2 if they are same. So if they are not same, you can return it from there, right? So it means they are not intersecting. So that is the first thing we have to check. Okay. So then when you are anyway traversing, you can always count the length of the string, length of the list, right? So that is what you also talked about. So
Yeah.
why we have to do that? Because this is the first pass, and then we need to find if which one is bigger. Because here, if you check, so this h2 actually smaller than h1 by 2, right? So if we were to start from h1 and h2, and then we won't be able to, even if we were um, you know iterating one by one step, we won't meet at the 7. So in order to meet them at 7, we can always chop off this portion of h1, right? you
Yeah.
know just ignore it. So how do we do is actually find the length of both these strings and both these lists, and so whichever is the longer one, we actually just make our pointer point to this position first, and then we start uh, yeah, traversing this both of the lists together, and then whenever it reaches the intersection point, we keep on comparing the node, the memory locations of the node, and if it is same, then we can return, right? So that is the approach you are discussing, correct, Shashank?
Yeah.
Yeah.
But let's say if we need to do that because we need to traverse, a linked list um, to to the end, right, all the way to the end.
Hmm.
And what if, like, we can traverse, and then at the end we reverse the that kind of, we reverse the linked list, right? Two linked lists, we reverse them, then we compare, because look at the picture, we compare once we reverse, the first node are the same, right? And
Hmm.
then we can move to the second node. The second node is two are the same, and we
Hmm.
move to the third one, that's
Hmm.
the same, right?
Hmm.
And we
Hmm.
keep move to the next one that different. Then we know that the previous one is the answer.
Hmm. Yeah. Yep, that's a good point actually. So we can have that approach also. Yeah. So, but the only issue of that will be if it's a doubly linked list, we can do it very easily, right? Uh,
Single linked list too, right?
yeah, we can do that too
Yeah.
with using more pointers, right? So, but then we'll
No,
have
the
to.
same pointer. We don't create extra pointer in this case.
Okay. So you are saying that we need to reverse it also, right? Here, at least the, or you are saying we should not. We can use a
Yeah, we
different way.
reverse it. We
Okay.
just go ahead and reverse
Right.
first linked list and the second linked list.
Right. Right. So yeah, either we explicitly reverse them, or we can also use a recursive function to do that. That also may be a possible option. Yeah. I think, yeah, that is also a good option. Yeah. So we just keep on traverse these both of these lists, and whenever we see both of them are different, in this case 6 and 9, so we can return the previous one,
Mhm.
7. Yeah, that's a good one.
The extra step is then, when we find it, then we have to reverse it again,
Correct.
right?
Correct.
To
Yeah.
get back to the
Yeah.
original
Okay.
linked list.
Yeah. Yeah.
But there's still big O of n.
Yes. Yeah, big opinion. In this case, also what has been discussed in the book, it's more passive actually. So that might be an optimum way one. What you're talking about. Yeah. Okay. So that is good. So actually, the book talks about the previous approach, or what we were discussing about, the Shashank was discussing. That's the only approach was being discussed. But yeah, that's a good one what you brought in. So this is what, and okay, in this question actually is trying to be more modularized, right? So what it's doing is first, you know, just get the sizes of both of them. Okay, so this function get tail and size. This is one function what is written here. Okay, implemented. So just run through the whole thing, list, and then you find what is the size. Okay, and then you return this result in the form of the head of the node and the size of the node. So that is what is returning. So this result is nothing but it is a structure, and that is what the structure is returning. So you get some sort of these two nodes, the for first and second list, and then just compare if the tail of both of them, okay, they are not same, because that is what we the first step what we need to do. So in this case, if the tail is both of them are not same, it means that they are not intersecting, and then you can return from here there itself. Or else, then we need to find whichever is the longer and shorter. So once we find whatever is the longer, we actually need to move the longer by that much difference. Okay, so therefore he's using the book is using another function called get kth node. Okay, so get kth node is nothing but whatever the integer value you are passing here, just forwarding that linked list. Okay, by k. That's what the get kth node is. Sorry, and then compare both the pointers, and if you have a collision, right, you just keep on incrementing, and if you have collision, return wrong. Okay. Any questions till now?
I think it's
Yeah, so this is the one which will take O of n, or maybe a b log time, right?
yeah
A plus b time, O of a plus
longer
b time.
length of list. Oh, yeah.
It'll be both, right? We'll have to traverse both the list. So okay. So if I think we have some more time, so the another very important problem what they're discussing.
So can we do this on fly? Is there any approach in one pass? Like what we discussed is two pass, right?
Okay. So how do you think about going for the one pass?
I mean, I'm just recalling somebody said in some of the lead code session, like uh, some method they were mentioning. I'm not able to recall something like calculating the difference. Uh, uh, I I'm not able to recall that, but
So if it is a single pass, so you can use a help of another data structure. That is one possibility, right? You put in hash set, one of the list, and then you start iterating through the next list.
well,
So that might be
I
one
feel
way.
I think they were reversing from back of the linked list, traversing from the one, and wherever they find the split, that time they told that, I mean, there was a, what you say, that is the point where the nodes are meeting. So it started from one, moved to two, then to seven, and after seven, the address will change for nine and six, right?
Okay. So you're talking exactly the way what Leon said, right?
Oh, okay.
Yeah, but if you do it that way, instead of reversing, you can use a recursive function. In that case, you don't even have to manipulate the list. You know, if we do it recursively, keep
Yeah,
going to the end, and then we see both the list are at the same location, right? So
yeah,
yeah, but in that case, both have to be of the same size, right?
exactly. No, but why will I mean, till seven address will be same, right? But the moment we find the address are different, then that means previous point was the intersection point, right?
Okay, but then to reach the end of the list, you still have to traverse it, right? Because
Traverse,
you're
yeah,
always given a head.
exactly. Yes,
Yeah,
that's the point.
yeah, yeah. But that's a good way of doing also. Another approach, and there will be many approaches, right? So
Yeah,
it's not that. Yeah. Okay, so there is one more problem, which is very popular, right? We have also been discussing in lead code this one about the loop detection, right? If
yeah,
it's given a circular linked list, okay, implement an algorithm that returns the node at the beginning of the loop. Okay, so if the what if we have a linked list which is what you say something like a corrupted one. Okay, so if we had something, okay, okay, so if we have something like 1, then pointing to 2, and this pointing to 3, okay, and then we have something pointing to 4, okay, and then we have 5, 6, 7, 8, something like that. Okay, I'm not going to write because my pen is not properly working today. So but if I come to 10 here, okay, and then I again point to this one, right? So here just assume that we have 5, 6, 7, 8, 9, 10. These are consecutive numbers, okay, right? So if we have to find this intersection, this is a very classical problem that we keep on discussing in lead code also, correct?
yeah,
So but why I'm actually want to refer this problem here also, because the way it has been discussed here, the method, it's very methodical, and I like the way she has gone here in step by step. Okay, so the first thing what actually she talks about here is detect if a linked list has a loop, right? So the first thing what we do is we start with a fast pointer and a slow pointer, something like that, and then we keep on moving. The fast will move 2 steps, slow will move single step, and then they will collide, right, eventually. Okay, but one good thing and very interesting thing what mentioned here is, like, some people might have a question, right? What if your fast pointer crosses your slow pointer? In that case it doesn't, how you can say it meets, someone will have a question like that, right? So how to deal with that? So what she says, if imagine if your fast pointer crosses your slow pointer. So what does that mean? Your slow pointer was on a location something like an I. Okay. Okay. So this was your slow pointer location. So what will happen? Your fast pointer will be at least at I plus 1, correct? So that is the only position when it can cross. Okay. So in order to prove that it actually will collide, right? And provided it's a loop is already present, right? So what she talks about is, before this step, what was the kind of state? So before this step, the slow pointer would be at I minus 1 location, correct?
yeah,
Okay, and this I plus 1 would be I plus 1, okay, and minus 2, right? Because it always jumps 2 steps. So this is a fast pointer, right? And this is a slow pointer, right? So if you evaluate this, it will be I minus 1 again. So it means they have already collided before itself, right? So because both are at the same location. So this is one way to prove. So that
So,
someone talks about, yeah. Go ahead, sorry.
I mean, when slow pointer is at I, fast pointer will be at I plus 2 or I plus 1. Only one cell difference it will be, right? Okay. At the second cell it will stand. So difference of 1. That's why I
Yeah,
and I plus 1, right?
yeah, yeah. So what is being said? Because some people, someone will surely say, okay, what happens when we are always discussing, okay, like when we are actually in this loop, it is going to collide. But someone will say, what happens if it jumps? Okay, okay, it skips that. So how can we prove that it will always collide and not just jump, right?
Santos, could you
Mhm.
explain one more time? I don't get.
Okay, okay. So what the book says, okay. So what is being discussed in the book is, right, if someone tells you us, like, okay, what happens, because in this loop it is always going to uh, collide, that is clear, right? But if someone says, so when you say it is going to collide, when fast pointer will be equal to slow pointer, correct?
Yeah.
So if someone says that what happens if my fast pointer, because it is actually jumping 2 steps, and my small pointer is jumping only 1 step, so there might be a situation, okay? So my fast pointer is a slow pointer is here, suppose, okay, and my fast pointer was here, okay, and so this was my fast pointer, and my slow pointer is here. So then my fast pointer will actually in the next step will cross the sky, right?
Yeah.
So this will be something like I plus 1, okay, and my slow pointer is here, okay, my fast pointer position was here previously, and slow pointer position current is here, and my fast pointer is now here, okay. So in this case, so how do we prove that it is actually colliding at the jth location? So that's very easy if you look at here, right? So we can always say that the at the j place, the slow pointer will be, the value will be I minus 1, okay. But now your fast pointer, which is here, at the previous step will be at also I minus 1 only. And how that is, like if it is I plus 1, right? And then it will always jump 2 positions at a time. So if you just subtract minus 2, right, from this 1, so it will be, if you evaluate this statement also, I plus 1 minus 2 will be I minus 1, right? So it will be pointing to this location.
Mm, okay.
Yeah, it's very simple thing actually, but she wants to be very explicit, and therefore someone comes up with, so how we can handle that question. So that is what is discussed, and I like that, so I thought maybe take it over here, right? Yeah.
And
So
one,
yeah, go ahead.
yeah, I was saying one confusion is like we take a dummy node and put initially both the slow and fast pointer at the same point and then
Mhm.
move, or should we put both slow and fast on the one itself?
No, actually, here it doesn't talk about that. You are saying that we should put the slow pointer before the fast pointer, something like that, right?
Yeah, yeah, yeah. Create a dummy node and assign both slow and fast to that, and then you start moving from there. In most of the implementation, I see like that.
Right,
So
right,
there
right.
is confusion.
So you can do it either way. You can actually even have a gap between both of them, or you can have both them start from the same place, but they still will collide.
Okay.
They should actually. Okay, so now the part of that, how to prove that this, okay, so I can't actually draw it properly here. So if we have something like this RK solution, right? So what it talks about, if we have this K, right? And if we are in this loop, okay, and so how can we find out that when we are colliding, we are just k steps ahead of this intersection, right? So this is where is the start of the loop, and that is what we want to find, right? So what it talks about is like when a slow pointer actually comes to k, okay, okay. So the slow pointer, if it comes to k, okay. So what will be the location of the fast pointer? It will be 2k, right? So it will be here, right? So it means if it is 2k, so uh, this k actually, so okay, this should be the k, and actually this should be your, okay, so this actually this distance will be the k, but this will be the fast pointer, right?
It
And
has
this will
covered.
be the k. Yeah. So how do we actually prove that actually it meets k values before? So our collision will be somewhere here. So this will be our collision, right? Okay. So, but if you look at the fast pointer location, and if we have a this loop, okay, this loop has something like a size of n, right? Okay. So this is the loop size, right? So in this case, we can, if we look at now, the f is always k steps ahead of s. Okay, this is one way, or we can say that f is equal to n minus k. Okay, so if it is following s, right? So f is always n minus k if we consider the size of loop as n. Correct. So if you look at this one, this distance, right? The other distance from this direction, okay, so it is n minus k. But if you look from this direction, it is just s is following k by s is following f by k. And if you look from here, f is following s by n minus k.
Yeah.
Correct. So now what happens if we want to actually meet both of these? So at any point when we are in a circle, so f is going to jump two locations at a time, and s is going to jump only one list at a time, right? One node at a time. So if you look at the difference, it is going to be only one. So as when both of them are traversing at each step, they are coming closer by one one node at a time, right? So they're always going to come closer by one. So in order for f to travel, if you want to actually close this gap of f to s, which is n minus k, so s will also traverse like n minus k, correct? And in that case, f will traverse 2n minus k. So that is the reason actually they will collide. So now if s starts, so this will be our location of collision. So if s is going to traverse this whole portion of n minus k, right? So that is what s will traverse. So therefore, s will always be at a location which is k distance ahead of the start point. So the collision will always be k distance before the start point. You got the point, because if f was here, and if you want to actually complete this from this n minus k, okay, that is we want to meet at the start point, because both of the distance is always reducing by only one element or one node at a time. So it will just take n minus k time for the s and f to come together, right?
So
So then,
your S is stagnant at its position.
no, actually that is fine. So if s is here, right, and if f is here, okay, so initially, so if what what is the way, what we say when we both of the pointers are in the circle, so and they are going to jump by their own speed or their own space, because f is going to jump at 2 by 2 and s is going to jump by 1. So the difference between both of them is going to reduce by one node at a time, right? Because 2
Yeah.
minus 1, okay. So in order for f to reach to the start node, okay, so s actually also represents the start node, right? Start node of the loop, okay.
Yeah.
So so in order to, what is the distance actually from f to s? It is n minus k, correct?
Yeah.
So if we want to reach that, because the difference actually is reducing by 1 always, so it will be n minus 1. So S will have to travel n minus k at a time. So when it travels, f is going to traverse 2n minus k, right, multiplied by 2. Then only they
Yeah.
both are going to meet. Okay. So indirectly S will be traveling n minus k. Okay. And that is what exactly it talks about, that when the collision point is actually k steps before the start of the loop.
Loop. Yeah.
Yeah. And then actually it talks about, you start the slow pointer with what you say, slow and fast pointer, you know, and you keep on moving the fast pointer twice the speed of the slow pointer and all that, right? So that is what the normal implementation comes to. Okay. So it's only the way we have to find. And then the other case will be like, what if our k is very big, and our loop is very small. Okay. So in that case, we can just take k modulo of our loop size. Okay. K modulo of our n, right? So that is
Yeah.
the only thing we have to worry about. So our k will change in that case, but we just have to take k modulo of n, and that is what will be our way to find it, right? So then how do we do is like create two pointers, fast pointer and slow pointer. Um, so yeah, we have the mathematical ways of proving that, right? So instead of that, how do we uh, actually even explain it logically? So that is one good way I thought, you know, was is explained in the book, right? So just this the implementation. I'll just go through it quickly. Okay, so this is one implementation. You start with the node. You have two pointers, right? And then find the meeting point. Okay, so just move the slow pointer at a single node and fast by two, and then see if both of them are at the same. Then you break. Okay, and then also check for an error case. In case if the fast is null or fast next is null, you return null. In case if there is no loop, right? Okay, or else then you start as use slow equals head, and then you have again move both at the same pace to find where it actually starts. Okay, and then so actually we are finding the collision point, right? So we just have to start one at a time, and then when we come here, so we return the fast pointer or slow. Anything should be fine, right? Okay, so this is a very easy implementation, right? But only thing is we'll have to explain
Proof
it
part.
how actually it is k distance ahead of the start of the loop, right? That is the only key point here. Correct.
Yeah, that proof part is very important. They ask in most of the
Yeah.
interviews.
So, but usually we go with that n minus k, and then we multiply by 2, and then we come up with that formula, right? So I thought that
Exactly.
the way she is explained in the book, it's very good because it's very simple. We don't have to go all the mathematical proofs, but it makes sense, right? If we have just its k distance before that, so how they meet it. So that the way it's explained in the book, I really liked it, and it's very easy to even understand and explain, right? So
Sure.
that's the reason I thought maybe just explain it here. Okay, so I think that's all what I had for this one, and I thought there was one more problem about the palindrome and also the reverse list, but I thought the loop detection is very what is a popular one, so I thought of going with this one. Okay.
So on line
Mhm.
262, uh, why do we have to check fast next equal no?
Fast next equals null. Okay, because
Yeah, because fast pointer is moving always by two steps. So if you are hitting
yeah,
the, you hit the what you say, null pointer exception. Like node will not be there, but still you are checking fast of next of next.
yeah,
That's
because
why.
actually while loop is actually terminating at considering the two cases, right? So either of
Okay,
this,
yeah.
yeah. So you have to check both the conditions. Yeah. Okay.
Yeah.
So I'll close for now. And thank you, guys.
Yeah, thank you
Thanks for
for.
being. Yeah. Thank you. So do
So
we